All right, welcome back to Math 1920, Calculus 2. We are in Chapter 5, Section 4, taking a look at exponential functions, their derivatives, and their integration. Okay, so we're going to look at the natural exponential function. All right, that's the graph of e to the x. Okay, it's the inverse of natural logs, right? We just got done looking at natural logs. Now we're going to take a look at exponential functions. Okay, and remember that they were inverses of one another. So if we did last section where we did composite functions, f of g of x and solved it and it was x, and we took g of f of x and solved it out to be x, right? They were inverses of each other. So we know that natural log and e, all right, are going to cancel each other out. So if we look here, we have natural log of e to the x. We can use rules of natural log, all right, and bring that x down in front, all right, using the power rule. And then we have x natural log of e. Natural log, the base is e, so natural log of e and e cancel each other out because they're 1, okay? So we end up with getting x. So this is how we're going to apply solving exponential functions here. So if we take a look at the definition of the natural log or natural exponential function here, the inverse function of the natural log function, f of x equals natural log of x, okay? We did that last section. Its inverse is the natural exponential function. We say f inverse of x is equal e to the x, stating that y is equal e to the x if and only if, all right, x equals natural log of y. At the bottom is that inverse relationship, and that's going to be very important for us when we are solving exponential equations here. Okay, natural log of e to the x is x, all right? Natural log and the e cancel. I'm looking at the left-hand side, the bottom left-hand side here with the inverse relationship. The natural log and the e cancel each other. Then we have e to the natural log of x is also equal to x because the e raised to the natural log of x cancels each other out and becomes 1. All right, so we're able to use these inverse relationships to solve exponential equations here. Okay, so if we want to solve this problem, we have 7 equals e to the x plus 1. Okay, so we can solve this by taking the natural log of each side. What I do to one side of the equation, I can do to the other. Basic algebra that you learned a long time ago. All right, so if we start with the original equation, 7 equals e to the x plus 1, and I take the natural log of both sides of this equation. Okay? Now, I can bring down that x plus 1 and put it in front because it's the power that's on e. All right, and then my natural log and e cancel each other out. Okay, so we have natural log of 7 is equal to x plus 1 because natural log and e cancel. Okay, then we subtract 1 from both sides. All right, so negative 1 plus natural log of 7 is equal to x, and then we can substitute into our calculator and get that equals negative 0.946. All right, let's do another example here. We have 8e to the x minus 12 equals 7. Now, before we start taking the natural log of both sides, simplify the equation down as much as you can. Try to get the e to the x all by itself. Okay, so first step is we're going to move 12. All right, so we're going to get e to the 8e to the x is equal to 19. Then we're going to divide both sides by 8. Now we're at a comfortable spot where we can take the natural log of both sides of the equation because we'll have a numeric value and we'll have our x that comes down because our natural log and e cancel each other. So now, just remember you have to do it to both sides of the equation. Okay, so we're going to take natural log of both sides. All right, and on the left-hand side, the natural log and e cancel and become 1, and only leaving the x. All right, and then we get a numerical value on the right-hand side of natural log of 19 divided by 8. So when all is said and done, all right, you can plug that into your calculator, and you get 0.865. So very simple. Do the algebraic manipulation to get the e to the x alone, and then take the natural log of both sides, all right, and then solve for the variable that's left. Okay, now if we want to solve a natural log function, we can use e to do that. Okay, so this is kind of going the opposite of the other one before. We're going to start with natural log. Okay, so if we have natural log of the quantity of 2x minus 3 is equal to 5. Okay, so in this scenario, we're able to put e on both sides of the equation or raise both of these sides to e. Okay, so we're going to take e on both sides. So what you do to one side, you do to the other. Okay, and we're going to take each one of those and make them the exponent for e. So I'm going to get e to the natural log of 2x minus 3 is equal to e to the fifth. Okay? We're doing that because we know that e and natural log cancel each other out. So when we do this on the left-hand side, all that's left is the 2x minus 3, and on the right-hand side we have e to the fifth. Now we just solve it like basic algebra. Okay, so you're going to add 3 to both sides and then divide by 2. And that'll give you a value for x that you can substitute into your calculator using the e button, okay, above the natural log button. So you hit second natural log, and you'll be able to get the e and plug in the 5. All right, and so on and so forth. So relatively simple. So if you have an e to the x problem, you're going to take natural log at both sides. Or if you have a problem like this that starts with natural log, you're going to raise each side to the exponent, all right, for a base of e, okay? Or take the base of e of both sides. Okay, so just remember some properties of exponential functions. They're really just the, the exponent properties that you learned in algebra. So as long as they have the same base and we're multiplying them, we add the exponents. If they have the same base and we're dividing them, we subtract the exponents. Okay, so basic review there. All right, so just a basic graph, okay? This is e to the x. The domain of e to the x is negative infinity to positive infinity, and we can clearly see the range is from 0 to infinity. It's continuous. It's 1 to 1 on its entire domain, which means there's no duplicate y values. We talked about that in the last section. Okay, it's concave upward on its entire domain. Okay, and if we take the limit as x goes to negative infinity of e to the x, it will go to 0. If we take the limit as x goes to positive infinity of e to the x, it's going to go to infinity. It's an exponential function. It's growing exponentially, all right, always increasing there. Okay, so those are kind of the basic properties that we just went over on the previous slide looking at the graph. This is just a slide for you to pause and make sure that you have it. All right, let's learn how to take the derivative of an exponential function, or explicitly the natural exponential function of e to the x. Very, very simple derivative to take. All right, the derivative of e to the x is e to the x. All right, it's itself. Now, if we take the derivative and we have some sort of u substitution we've done, it's going to be e to the u times the derivative of whatever that exponential stuff is. Whatever the exponential argument piece is, it's going to be multiplied by the e to the x piece. So let's take a look at a couple examples here of how to do this. So the first one, we have y equals e to the 2x minus 1. Okay? So when we do that, the derivative of e to the 2x minus 1 is going to be e to the 2x minus 1 times the derivative of 2x minus 1, which is just 2. Okay, so our answer will be 2 e to the 2x minus 1. Okay, and then we'll do the other one on the right. Okay, we have y equals e to the negative 3 over x. All right, so in this case, it's going to be e to the negative 3 over x times the derivative of negative 3 over x. Okay, so you'll have to rewrite that x is x to the negative 1 and put it in the numerator when you do that. Okay, so you end up getting 3 to the x minus 2. Okay, and then it goes back down into the denominator. So make sure that you choose u if we have to use that u substitution to be whatever the exponent is. Okay, so you're going to get e to whatever that exponent is times the derivative of the exponent. In this case, the derivative of the exponent is 3 over x squared. All right, so you'll see that. So let's break one down a little bit more here. If I ask you to find the derivative of y equals 5e to the x squared plus 5. Okay, so very simple here. We're going to use u substitution. All right, when we do this. All right, so first we want to pull out that constant. So we know that this is going to be a e to the u du type function. Okay, so I'll pull out that constant in front. So it's our derivative will be 5e to the u du over dx. So now we have to choose u. U is going to be x squared plus 5. Okay, so du is going to be 2x dx. And we have to rewrite du in the proper form of du over dx so that we can do our direct substitution, since we've already taken the derivative on the left over there. All right, when we do this. So du over dx is 2x. Okay, so when we write this out, we get 5 e to the x squared plus 5 times 2x. Okay, and when we simplify that down, we can say y prime is 10x e to the x squared plus 5. So really, guys, it's really easy. It's going to be e to whatever it is. So in this case, e to the x squared plus 5 times the derivative of whatever that exponent is. The derivative of x squared plus 5 is 2x. Okay, and then we had that 5 out in front that's a coefficient. So, e to the x, very simple derivative for us to take a look at. Now, let's step into doing the integration. Okay, so the integration rules are the integral of e to the x is, surprise, e to the x plus c, right, because it's an indefinite integral. Or if we have e to the u du, right, we have to, have some other stuff in the exponent here. It ends up being e to the u plus c when we do this. All right, so we'll do a couple examples here. First one, we have the integral of e to the 3x plus 1. So in your mind, you're like, all right, I know this. U has to be 3x plus 1, okay? And then my du has to be 3, right? And then I have to rewrite that so that it works out when I do my replacement. So I know that I'm going to end up with 1/3 e to the u du, right? Because du is 3 dx, and we have to replace dx, so it'll be du over 3 is equal to dx when we replace that. Okay, so we get 1/3 e to the u du. We do the integration, so you're going to get 1/3 e to the u plus c, all right? And then we have to replace our u with what it originally was, 3x plus 1. So we get e to the 3x plus 1 divided by 3 plus c. Okay, last example here. We have the integral of x squared e to the x cubed. Okay, so make sure that you're understanding, we've got to do some u substitution here. And generally, all the problems that we're going to do work out pretty good. So we choose the exponent, right? So u is going to be x cubed. That means du is 3x squared dx, okay? We're only looking to replace x squared dx, so we have to move the 3 to the other side. So we say that du divided by 3 is equal to x squared dx. So now we can replace everything. We can replace the x cubed with u. We can replace the x squared dx with du over 3. Okay, and then we're ready to set up our integral. We're going to factor out that 1/3 in front of our integral. So we're going to have 1/3 the integral of e to the u du. Very simple integral for us. This ends up being 1/3 e to the u plus c. And then we have to replace our u back with what we originally had. All right, and we get 1/3 e to the x cubed plus c. And we're going to do a lot more detailed examples in class. This is a good overview just in case you missed class or things like that, so that you got a little bit of background on what we've been doing in this section. All right, else email me with any questions, or I'll see you in class. Have a great day.